Okay, so as we talked about outliers having a lot of different options, normality is kind of the same. There's a lot of options in checking for normality, and I'm going to start with the basics. So let's go to Analyze, Descriptive Statistics. We're going to go into Explore, and then we're going to move our variables over. I'm just going to do the first one again over there. Then I want to look at plots. Here, I'd like to check the normality plots with tests. And then, let's see. Also, we want to see the histogram. All right. Okay, so then we're going to hit OK. And this is going to show us a couple of things. So the first thing to notice is this does list skewness and kurtosis here. We have our statistic. We also have the standard error rate. Now, those are important, and we'll talk about those in a little bit, but those are important. We can't necessarily take that at face value. We have to divide this and then get another number, which we can use. So we'll talk about that in a minute. The Kolmogorov-Smirnov and the Shapiro-Wilks test. These are, well, the Shapiro-Wilks test is one that a lot of people use. So this is one that you could trust to let you know if the data has a normal distribution or not. The Kolmogorov-Smirnov test, actually people say don't use it at all. And in this case, they're giving you the same values, but sometimes you'll see where one has significance and one does not have significance. So that's something to think about and then just keep note of. If that's the case, always go with Shapiro-Wilk. Never go with Kolmogorov-Smirnov, also known as the KS test. So in this case, what it's telling us is that because this value on the Shapiro-Wilks test, the sig value, also known as the p-value, is less than 0.05, there's a non-normal distribution. So it's backwards of what you would think. What that's doing is telling us that we can fail the null hypothesis. And with failing the null hypothesis being that there is normal distribution, then we're just basically saying if this is non-normally distributed data. And you can tell, it's heavily skewed to the left, and so it's non-normally distributed. Now, so that's a key, the Shapiro-Wilks test, that's important. We want to know that one. Looking at the histogram, this is important too. It lets us see the skewness. We can also take a look at that with a bell curve. So I'm going to show you how to do that. All right, go to Analyze, Descriptive Statistics, Frequencies. Let's move our variable over, hit Charts, hit Histogram, and show normal curve on histogram, and then hit OK. All right, so that lets you see the bell curve there, and we'll talk about these in just a moment. Okay, so going back up to the first test, we've got the histogram here at the top. You'll have that histogram at the bottom with the bell curve overlaid. Let's go back up here just so we can follow along. So here we have a QQ plot. And typically you want to see your data hugging this line. So you can see it hugs it pretty good here, but these are not hugging it. So that would give an indication that there's non-normal data as well. And as noted, again, the Shapiro-Wilks test, this QQ plot, the normal QQ plot, those are two popular ways of saying that your data is normally distributed or not. You have this detrended chart QQ plot, which is calculated a different way than the normal QQ plot. So I don't use this one that often. Then you have your box plots, which, as we've talked about, these are helpful with the outliers, but not so much with normality. Okay, so here we have the bell curve. So let's talk about the bell curve. Okay, so with your bell curve, this outline is basically what we want your data to fall within. So when we have data that's coming outside of this, then we can pretty confidently say it's not normally distributed. Now, see, you've got some down here, which would be your negative skewness, and then you have a little bit here. So these wouldn't be a big deal, but really you've got this other that's up here that's pretty big. So just looking at the picture here, we would say it's not normally distributed. Going back to the top and we look at the QQ plot, it's close, but not quite normally distributed. And then looking at the Shapiro-Wilks test, because that's a significant value of less than 0.05, we say that the data is not normally distributed. Okay, so now I want to look at skewness and kurtosis. Okay, and looking at skewness and kurtosis, we can go back to your descriptives table at the top. What we have to do is divide the skewness number by the standard error. So you'll see here, I've got the statistic and then the standard error. And we've got the negative 1.317 and then the 0.130. And then here we have the 1.987 and the 0.260. So I've divided those two. If you're not familiar with how to do that, go ahead and you can enter and divide this by that. Notice I've used a slash for the divide. And then you can carry that down. So what we know here is that when that number is above positive or negative 1.96, then there's concern. Now, some say that that isn't a huge concern until it actually gets to 3 or more. Then it's a big concern. So in this case, I think we have enough information to verify that this is non-normally distributed data based on skewness and kurtosis. Now, I do want to show you how to get the graphs for that. So let's go to Analyze, Descriptive Statistics and Frequencies. I'm going to reset this, move this over. You want to uncheck that display frequency table, go into statistics. You can check both at one time if you want, or do one at a time. Hit continue, then go to charts. In the charts, you want histograms and then show normal curves. We're going to get that same diagram that we received before, but that's okay. And hit okay. All right, so this gives you the numbers once again. And then we also are getting this image once again. But basically for this, what we're most concerned with is dividing the skewness number by the standard error, and then also dividing the kurtosis number by the standard error. If it's above positive or negative 1.96, then we have reason to reject the null hypothesis that there's no skew. In other words, we're saying that because of this number being above 1.96, then we have non-normally distributed data. And then with this, you can visually see that the data is skewed to the left, meaning it is negatively skewed. And then also the with the kurtosis number, when it's larger than 3, it's called leptokurtotic is the name distribution, meaning it's just larger than 3. So I'll put that information in your notes, but that's basically confirming, at least for this first variable, that we have non-normally distributed data. The reason it's important to know if your data is normally distributed or not is because we need to be able to select the appropriate test. So normally distributed data is called parametric, and then non-normally distributed is called non-parametric. So as you go through here, you'll see, for example, if we're doing correlation test, we want to know if there's a relationship between two variables. If we have parametric data, meaning it's normally distributed, we can use Pearson's R. If it's not parametric or not normally distributed, we use the Spearman's test. The same goes down here with, let's see, if we're comparing groups and we want to decide between ANOVA or Kruskal-Wallis, that will depend on if you have normally distributed groups or not. So we'll get into that later, but I just wanted to give you a reason for all that you've gone through today with the test for normality.